Hello guys, this section is about velocity and acceleration, section 1.4. Velocity and acceleration are both vector quantities, and in this section you're going to see some similarities and differences between those two vector quantities, how to add and subtract in two dimensions. Let's review a little bit about vectors, and that applies to velocity as well. So when we are adding two velocity vectors in two dimension, the vectors not always point due north, south, east, or west, or positive or negative side of the x and y coordinate. It is going to be random, like any direction. So resultant vector is a vector that results in adding two or more given vectors, and that applies for velocity as well. So we can add vectors using tip-to-tail rule and parallelogram rule. So instead, we talked about this as a displacement, but that is applying for any vector as well and velocity as well. Let's say that we have two velocities, one E and one D, and in this case, there are two vectors. How to use the tip-to-tail rule. Exactly the same that we learned before. You can just move or slide the vector E where the tip of the vector D is, and then you can join the tail of the vector D, which is the first one, with the tip of the vector E, which is the last one. As I said, you can have two or more vectors adding together, and using the same rule, tip to tail, that will work. Another rule that is specifically useful when two vectors are at the same origin, like in this case, E and D are in the same origin. So that would be useful and time saving if you draw from a tip of both vectors parallel to the other vectors. So from a tip of E parallel to D, and from tip of D parallel to E. When those two lines intercept, that will be a tip of resultant, sum of those two vectors. So in this case, vector F is equal vector D plus vector E, and it starts where those two vectors starts and ends when those parallel lines intercept. Now, adding those vectors graphically, as I mentioned, let's do a practice. Tip to tail, you have vector A and vector B. That can be velocity as well. And then you can actually leave the vector A where it is and move vector B parallel to itself where the tip of the vector A is, and then join tail of the vector A with the tip of the vector B. Remember, when we add graphically vectors, you can add more than two vectors. And another thing that you need to remember is don't forget the scale. The scale is very important. So as I mentioned before, if you draw a vector that is too big, you can find a reasonable scale in order to find the space. Use the space that you have to draw a vector or a set of vectors. So we want to add velocity together using component method. But we already just learned that adding displacement together using component method. But velocity and displacement are both vector quantities, and everything that we learn about displacement applies to velocity as well. And guess what? That is exactly the same. So if you have velocity v1 and velocity v2 and you want to add it to get total velocity, you do the same thing. You resolve velocity 1 into component x and y, and you resolve velocity 2 onto component x and y, and then guess what? The same thing. Add all y's together, you get total y, and you add all x together and you get total x. And then that's pretty much the same thing. You can use a Pythagorean theorem and tan negative 1 to get magnitude of the total velocity and direction of that. So that is very, very similar what we learned already. To summarize, for any vector addition using component method, it applies for a velocity or displacement for any other vectors. So what we have, if you have two vectors, like in this case, you can resolve those vectors in x and y. You add all x's together and all y's together. Then you can draw it. It's very important to draw it because that's how you get an idea what you're expecting. Then use a Pythagorean theorem and the tan negative 1 to find magnitude and the direction, and then you state it whatever you get for both of them. Now here is an example, adding two velocities together. First, we have a motorboat steers straight across the river at a constant velocity of 12 kilometers per hour north. The river is 0.3 kilometers across, wide. If there is no current, how long will it take to cross the river? And remember that I'm going to draw your attention to constant velocity. So it's a simple velocity. It's a simple solution. So what we have is on a y-axis, you have that boat speed. It's 12 kilometers per hour north. And the delta dy, which is a wide, how wide is the river, is 0.3 kilometers. So time to cross a river is distance over time, or displacement over velocity, but both of them are in the same direction. So either velocity or speed is used interchangeable, and distance and displacement also. So we have 0.3 kilometer and 12 kilometers. So if you see that 0.3 kilometers north and 12 kilometers per hour north and north cancel. So that's why I didn't even write it there. So time is 0.025 hours or 90 seconds. So if there's no current, that how much it takes? 90 seconds to cross the river. So what is total velocity if there is a current? In this case, the current is 24 kilometers per hour east. That's a good thing, is like a perpendicular, is easy. So what you do is what is given, what is required. Vy is 12 kilometers per hour north. Vx is 24 kilometers per hour east. And total velocity is required. So find the direction, which is Vx over Vy. 24 divided by 12 kilometers per hour actually cancel. And it's a 63 degree. So theta there. And you see that is a wide, so theta is a 63. And then you can use Pythagorean theorem to find the magnitude of total velocity. Remember, it's like a c squared is equal to a squared plus b squared, same idea. And then plug those numbers there. You don't really need to convert if you want to convert it, you divide it by 3.6 to convert kilometers per hour to meter per second. So it's a 26.8 kilometers per hour or 7.45 meter per second. Now, the interesting thing here is that how long will it take to cross a river if there is a current? So velocity of a river, water current, is Vx 24 kilometers per hour. Remember that we did it before when it was no current. So when it's no current, so a boat is going to go straight up. There's no problem. However, when it's a current, it is going to be on direction of the final velocity, and the boat is going to end up somewhere here. So how long will it take for the boat to come from this side to this side? So it's crossing the river, but it's crossing a river in a wide way, in an angled way. It's not straight up as before. Let's see if that make any difference at all. So what we do is, since that is a constant velocity on both sides, river is a constant velocity and boat is constant velocity, we'll give you a constant velocity as well, total velocity. We already calculated that total velocity, but let's see if we can use it or not. So time is total displacement over total velocity to get total time. Okay, now here is an interesting thing. This one actually is a hypotenuse for velocity, and this is a hypotenuse for displacement, the whole thing. Now, this one actually is delta dy, which is adjacent, over cosine theta. Hypotenuse is equal to adjacent divided by cosine theta. That's trigonometry, is true. The same thing applies for velocity total. So velocity total, which is a hypotenuse for velocity triangle, the small triangle, is equal to this component of velocity, which is adjacent of this angle, divided by cosine theta. But if you see, cosine theta and cosine theta cancel. And then what we have is a delta dy over vy, which we had it before. So that means 0.30 kilometer divided by 12 kilometers per hour. So kilometers per kilometers and north cancel. What we have there is a 0.025 hours, and that means it's 90 seconds. It's exactly the same. That's an interesting thing, because that is like a misconception that if there's a river flowing, faster the river flowing, harder it is to go across, because let's say that you're swimming. Let's say that you're swimming across, and there's a river there just flowing. So that is exactly the same if you want to cross the river going from one side to another, even if the river is not flowing at all, there's no current at all, or there's like a very fast, might not be safe, but the time that you cross from one side to another side is going to be exactly the same, because that component here will help you to go further away, travel further, but actually what makes the difference from going from one point to another side of the river is only y component. And you're going to see that in a projectile motion later on, that horizontal, sometime in that in a vertical displacement will not make any difference at all. So those are pretty much independent motions as well. So that's about this adding velocities in two dimension. This is an easy one, but you can have any direction, adding vectors at any direction, the same way as we add displacement before. I'm going to draw attention to subtracting vectors, because sometimes if we need to calculate acceleration using scale graph diagram, which is really rarely used, you can actually find a change in the velocity, not velocity, change in the velocity by subtracting initial velocity from final velocity. Remember, change in the velocity is v final minus v initial. V final minus v initial. So that means that you can subtract v initial from v final. But let's do in a general way, how can we subtract two vectors? If you have a vector A and you have to subtract the vector B from A, what you need to do, you add the opposite of vector B. So it's going to be A plus minus B. And you're using that tip to tail rule, exactly the same as you're adding any two vectors. So you start the vector D, which is A minus B, is going to start where the first start and is going to end where the last ends. So in this case, minus B vector, the opposite of B, is the one that is the second one. Okay, so here is another one example. So you leave A as it is, you flip B, and then using a tip to tail, starting from A, and join it where the B ends. Pretty much the same as I mentioned it. So remember that this is if you need to calculate change in velocity using that graph, scale graph diagram. Yes, true, it's pretty much is not used at all most of the time, but it is good for your knowledge to know how to subtract two vectors. Remember that when you calculate change in velocity, it's about v final minus v initial, not v final plus v initial. It is about change in velocity, it's not total velocity. Don't get confused with the previous section of this lesson. To calculate acceleration in 2 dimensions, obviously the most useful method is using component method. So here is an example to make you understand how to calculate acceleration. A ball is hitting the wall with initial velocity of 6.2 meters per second, west 25 north, and bounced at a final velocity 5.8 meters per second, north 30 east in 0.05 seconds. What is the acceleration of the ball? So in order to find the acceleration of the ball, you have to find what is change in velocity, because after that, everything is easy. You just divide it by time. But let's focus on finding change in velocity, because it's 2 dimension, is not that easy. So in order to change, in order to find change in the velocity, you can draw the vectors first. Make sure you draw it nicely, proportionally. You don't need a ruler or protractor, but at least you know you can draw approximately the angle, approximately the length, proportionally as well. So let's say that the vector v initial is longer than v final. So that's why we draw it a bit longer, because it is not really that much, 0.4 bigger, longer. And here is a 25 and other one is 30. So we draw that 30 a bit wider than 25. And then what do? Draw and label their components. That's very important. It's a component method. So x and y component, label it. And x and y component for final velocity, and label it. It's very important to label those so you know what you're doing. And then you can calculate component method of v initial. So one more time, using that SOHCAHTOA or using what you see or in the front of angle, whatever method actually works for you, make sure you don't make mistake, because that mistake here will carry over to other calculation. So v initial x is beside the angle, so that anything beside adjacent use cosine, and everything on the front, so that opposite of the angle, it is using sine. So that's why v initial y use sine and v initial x use cosine. You calculate it, and remember that this is on a second quadrant. I already explained that x component on a second quadrant vector is negative, and y component is positive because it's up. It's the same along the positive direction of the y-axis, and this is negative because it's the opposite of positive direction of the x-axis. So that's why those are reflected here, and those signs are very, very, very important. Next one is do the same thing for V final. So for V final, X is in front of 30 degree. In front of 30 degrees. So that means use sine, and Y is beside the 30 degree, use cosine. Both of them, since that is in a first quadrant, both components are positive. After you have calculated X and Y component of V initial and X and Y component of V final, you group X's together and Y's together. Remember, signs do matter. Don't forget signs. And another thing is, don't forget that you are not adding them up. You are subtracting V final X minus V initial X to get change in velocity on X axis. And we do the same thing, V final Y minus V initial Y, to find change in velocity on Y axis. I know that many people do that mistake. That is something that you have to pay attention. Do not add if you need to calculate acceleration. So that's what we do. Make sure that signs are there. So if you see that is a minus and minus become plus, that's why it's a big number here. And other one is subtracting, because that is a plus and minus. Here it's just subtracting, and it's a 2.4. So both of them are positive. And another step would be draw them. And since that they are both in positive, you just need a first quadrant to draw them, because both of them are in that quadrant. So you draw them. Make sure you draw them proportionally, because now 1 is 8, is long, much longer, almost 4 times longer than Y component. So it gives you an idea of angle. So angle is not that big. And the hypotenuse, since that Y component is not that big, is not going to make a big difference, big change. So expected value is going to be somehow between 15 degree of the angle and between 9, around 9 for hypotenuse. So let's see how it goes. So label those, and we're looking at hypotenuse, which is a delta V, and delta V is equal square root of delta V x squared plus delta Vy squared. That is equal to square root of 8.52 squared plus 2.4 squared. That is 8.85, so closer to 9. That's what we predicted. And the tan negative 1 to find the angle, and the angle is 15.7, like a 16 degree. So that's pretty much what we have for, and you can, this last step is, as I said, is just very easy. After you have magnitude and direction of the change in velocity, what you need to do is to divide by time. Remember, this direction will carry over to the acceleration direction. So make sure you write that, because acceleration as a change in velocity is a vector quantity. So direction matters. So you carry that over to the side. 15.7 is angle. You can round it to 16 if you want, but that's most important thing, to find things accurately. And that's about it, about the velocity. And that's about it for this lesson. You finally got a short lesson. Enjoy, learn, and I hope that we'll see you next time. Have a good one.